Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's MD plus DI webinar, Production Under Pressure, Why Vision and Manual Inspection Are Failing You, sponsored by LaserLinc and broadcast by Informa. I'm Michael Krieger, and I'll be your moderator today. We have just a few housekeeping announcements before we begin. First of all, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about our speaker, download resources, share this webinar, and most importantly, participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and toward the end of our webinar, we will ask you to complete our survey. Please take just a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen or type your issue into the Q&A area, and we will be glad to offer one-on-one assistance. And now, on to the presentation, Production Under Pressure, Why Vision and Manual Inspection Are Failing You. Our speaker today is going to be Chad Walker, Product Manager at LaserLinc, and to learn more about him, you can visit the Speakers widget. But before I turn it over to Chad, I want to put all of you to work with our first polling question of the day. So let me ask that to you. What brought you here today? Is it exploring new defect detection technology? Are you just not satisfied with your current inspection method? Are you losing too much product to scrap? Do you want to improve product quality and consistency? Or is there some other reason you're joining us today? And if so, please do me a favor and just type that into the Q&A area so we can understand what's bringing you here today. And with that, Chad, thanks for joining us. Over to you.
All right, thank you. Today we're going to be talking about quality control for production process. We're going to focus on medical extrusion, but this talk can be applied to any continuous production of mostly round product, wired cable, hose, tube. And we're going to talk about measurement and defect detection. And we're going to go into a case study for a prominent medical tubing manufacturer and discuss how we were able to improve their quality control. So first, let's talk about traditional inspection technology. Most medical tubing lines have laser micrometers used to measure the dimensions of the product, as well as do defect detection. Lately, vision inspection has been very popular, but of all the critical medical extrusion, I find all of them are using human, tactile, and visual inspection because it is more reliable than the laser micrometer or vision system. We'll talk more about why that is and why it's still not enough. So some reasons why inspection is challenging. More and more, we are getting more challenging materials to extrude, and some of these materials they degrade over time. So you are more likely to produce defective product, which means you have to catch more defects. And quality standards are also getting more rigorous. So a customer of yours might demand higher quality than you've seen in the past. And both of these are driving more robust defect detection that traditional inspection methods fail to achieve. And when you fail to achieve 100% inspection, you can have issues like not making sales, your customers reject product, and you don't make the money. Or it could be reputational damage. You get a reputation that you're making defective product and your customer moves somewhere else. Or worst case scenario, that the defect actually is critical and harms somebody, and the FDA gets involved, recalls your products, and potentially you could have lawsuits for those issues. So we're going to talk about a major medical extrusion manufacturer and how we were able to overcome some of these challenges. So first, let's talk about why the traditional inspection fails. Again, we're talking about measurement and defect detection. So I'm going to explain why they fail for both cases. Laser micrometers work by projecting a laser onto a part, and you can see that on the right here. The red represents a laser that goes from left to right. It's hitting this black part and making a shadow. And you measure the distance between the two edges of the shadow. That is how you measure the diameter of your product. But you can see that this is very limited measurement. You're measuring the distance between 2 points, which means there is a lot of room in between those 2 points that is effectively blind. The micrometer does not see it, and it cannot measure that aspect of that product. We call this shape error. If your product is not circular, the measurements vary with orientation in the measurement field. And this leads to first problems with measurement because you can't tell if your product's in spec or if it's just non-round and at a certain orientation. Or if you're doing defect detection with micrometers, you're looking for a change in diameter over a length. And if your diameter changes based on the part's shape and orientation, you're digging into your ability to see real defects that change the diameter because you have all this noise due to shape error. So that's some of the limitations with a laser micrometer. Sorry. Vision systems, they measure diameter in a similar way to laser micrometers. So it takes a picture of the product and it finds the edges of the product and measures the distance in between. So similar to a laser micrometer, that's going to lead to shape error when your product is non-circular. All of the information in between those 2 points is lost. So your measurements are potentially not accurate. And we'll dive into that a little more later. But defect detection is slightly different for vision systems. You're looking at a change in the image, either from image to image or along different aspects of the image. For example, maybe we're looking at a column of video footage, and we can see that the color changes as you look up in that picture more. And maybe that change in the image or the color is a threshold, and if you cross that threshold, it's a defect. But this is very hard to imagine. What is my defect going to look like in terms of a color change or an intensity change? It's not easy for humans to know the correct threshold there. And it's also challenging to get a uniform lighting and detect normal surface variation that's acceptable and not trigger a false positive. So in my experience, vision systems have been all the rage for the last 15 years, but everyone who buys them, they get frustrated and they end up in the corner. And they're just not reliable. They create too many false positive defects, and they might miss critical defects. So again, manual inspection is what I see is the fallback position. It is the most reliable inspection method. But we all know that manual inspection is subjective. I might see a defect and my coworker might disagree that it's a defect because they have a different opinion on what is a defect or not. And it's inconsistent. Maybe in the morning I catch something, but after an 8-hour shift, I'm tired and my fingers are not feeling as sensitive as they used to, and I miss defects. So it's very inconsistent. And the fact is you cannot feel all defects. And I have an example here that we'll talk about in a moment, but it's this little drag line, a small valley in the extruded material, and you cannot feel it. It is just too small to feel. This inspection is done after production. So maybe you're producing, you're bagging parts, and it goes to the inspector and they inspect it. 20 minutes later, they say, hey, you're creating a bunch of defects. We need to fix this. You've already done 20 minutes of extrusion, and that's all waste. So it's just not real time. It's also expensive. I've seen an operation with 40 full-time inspectors. Some of them are doing what they call 300% inspection, which is 3 operators looking at every single piece. So it's extremely expensive.
Let me put all of you in the audience back to work. We have another polling question for you today, which is, Do you currently rely on manual inspection in your production process? So please respond with one of the following. Yes, it is still our primary method. Yes, but only for occasional spot checks. Rarely, we mostly use automated inspection, or nope, we've fully moved away from manual inspection. And while you take a moment to respond to that, I will turn this back over to Chad. Chad, go ahead.
All right. So we recently did a case study with a prominent medical tubing extrusion facility, Microspec. They were founded in 1989 by Tim Steele, and they're known for producing complex geometries, multi-lumen extrusions, and exotic materials. And we're going to talk about one of their hardest challenges. So this case study involves this white product here that was being extruded. It was a unique material they've never extruded before. Their customer demanded that it be this material. That material it produced a lot of defects over time. Basically, the material got degraded over time, either in the extruder from too much heat and friction, and you would get burnt pieces of plastic that built up on the edge of the extruder and caused issues. Here are some of the defects you can see: a bump, a burnt gel in the plastic, small pit, and a drag line. At the time, they didn't even know they were producing drag lines, and we'll talk about that more in a moment. They relied on 100% manual inspection, so they had operators feeling the parts, and they were using a laser micrometer. So when they first started this project, they made a batch of parts, and they gave it to their customer, and that customer rejected it. And they said, we found 40% of the parts had defects on it that we consider unacceptable. And this was the challenge that LaserLinc came in with, trying to get that number down to as close to zero as possible. And we did it with a technology called laser line triangulation. So laser line triangulation is different than a laser micrometer. It projects the laser onto the part, and there are sensors that triangulate the position of the laser, and it creates a 3D surface model of your part. So effectively, this is a non-contact CMM, coordinate measuring machine. And for those that don't know, a coordinate measuring machine is a contact device that has a probe, comes in and touches the part hundreds of points around the circumference to build up a map of the product. Laser line triangulation is effectively a non-contact, high-speed CMM, coordinate measuring machine. So on the left here, you can see the three lasers come in on the product, and it builds this 3D map as it goes through. You can measure directly diameter and circularity of your product, as well as do dimensional defect detection in a way that you could never do with a micrometer or vision system. So we installed our laser triangulation device called FlawSense in the Microspec production process. And I was on that installation. I got to see it run. For the first hour, I was very impressed with the results. But the interesting thing came up about an hour into the run when we started detecting continuous defects. And at the time, they had quality inspectors double checking the results of FlawSense, and they could not find the defect. So I'm concerned because my device is detecting stuff continuously. Their quality operators say it's not real. I rerun the parts through FlawSense. I see the same thing, but I'm looking closer and I see that the defects are this continuous line of yellow points. Yellow means that we're finding an indentation, a small divot in the product. So I knew it wasn't going to be a bump. It was going to be a line of a valley, basically. We looked closer with magnification and we found the line. It was a drag line. And when we showed this to the operator, he realized that that came from a gel on the extruder head, that a little piece of burnt plastic was dragging into the edge of the extrusion, creating this line. The line was so small the quality inspectors couldn't see it. FlawSense saw it. and the operator knew the problem. He went and cleared the extruder head, and the defect went away immediately. So this problem would have gotten worse and worse over time as the gel got bigger, and eventually it would have broke off into a gel that was in the surface of the product. FlawSense told them that was happening before anybody else knew, and they had the opportunity to stop it so they immediately could start making good product again so they could sell product, but also preventing this issue from getting to their end user. So after a month, they saw a reduction in defects from originally 40% in this really high spec unique material application down to less than 1%. And it changed the game for them. They were able to sell this product now. And because of that, they paid the entire cost of the FlawSense off in 9 months by achieving less scrap and selling more product. You can learn more about this at laserlinc.com/defect detection. There's some great quotes from Tim Steele, the CEO. So this was a huge improvement to their production process. But that's just defect detection. We're also talking about measurement. And when I was on this installation, talking to their team, I learned about some of their other challenges involving measurement. So they produce multi-lumen products that are mostly round, but not exactly round. And they were struggling to measure dimensions of this product. They were using a 3-axis micrometer as well as a single-axis micrometer that rotated the part to 8 different orientations, effectively mimicking an 8-axis laser micrometer. And when I saw this product, it immediately was apparent to me that they have a shape error issue trying to measure the dimensions of this with a laser micrometer. And it's provable. You can actually simulate what the measurement results will be of this shape in a laser micrometer. So I did that. I took the DXF file from this shape and I ran it through a simulated 3-axis and 8-axis laser micrometer. Now they have specifications, their spec ranges for height and width are 6 thou, so they want to make sure they're within plus or minus 3 thou for height and width. And the difference between the max and min height and width needs to be under 4 thou. So with that in mind, with those specifications, is it possible to measure this shape with a 3-axis micrometer or an 8-axis micrometer? Here's the simulated results. If I put this shape in a 3-axis micrometer and I rotate it, the measurements vary by 1.4 thousandths of an inch, which is 23% of the diameter spec range. That is potentially acceptable, but not ideal. You want to be ideally 1/10 the spec range in terms of the error of your measurement device. And keep in mind, this is a simulated situation, so it's the best case scenario is going to be 23% of the spec range is error due to shape. Now, 8-axis is acceptable. The diameter is consistent at orientations. But the real problem is with ovality, or max minus min dimensions. So they want to know the height and width of this product. In a 3-axis micrometer, if you rotate the shape in a 3-axis micrometer, the measurements vary by 5.4 thousandths of an inch, which again, compared to their 4 thou spec, is well beyond the spec range. To put it another way, you could be out of spec just by rotating the part, not changing the dimensions. All of a sudden, you're reading out of spec. Absolutely not acceptable, and just asking for issues if you use micrometers to measure this product. Even with an 8-axis, measurement varied by 78% of the spec range. Again, completely unacceptable. You want to be 10% ideally max of the spec range. So how do we improve this? Well, we use FlawSense, laser line triangulation, because again, it's like a non-contact CMM. You can measure the contour, the full 360 shape of this product. And on the right here, you can see this rotating shape. This actually comes from Microspec's 3-lumen tube. And you can see how we're measuring height and width, that pink box, at all orientations. As it rotates, the pink box dimensions do not change. We are accurate to 5% of the spec range. Compare that to 78% with an 8-axis micrometer. Laser micrometers are nowhere near as accurate as laser line triangulation. And on the left here, you can see another example where they're trying to measure diameter of a 3-strand, in this case, jacketed wire. And there's 3 circles here. The outer circle is the minimum circumscribed circle, which is the smallest circle that contains the object. The inner circle is the max inscribed circle, which is the largest circle that fits inside that shape. And the difference between these two is the circularity of the product. So we're directly measuring circularity in a way that laser micrometers never can. We also have a best fit. So just showing you that there's many ways to measure these shapes when you have a 360 continuous contour measurement. And again, it gives you superior measurements regardless of shape and orientation of your product. So I'm going to recap why laser line triangulation is superior. For defect detection, it's dimensional defect detection, which means you're looking for changes in the dimension of the surface, a rapid change in the surface height, and if it crosses a threshold, it's a defect. It's not subjective, and it's easy to understand the dimensionality of defects, height, width, and length. It's real time, so it's up to 10,000 frames per second, which means we can catch defects that are very small in length, and it's real time. There is very low latency in between the measurement and the decision of a defect or not, and we send that decision to sorting machines or paint markers, or we can stop our respool line, basically ensuring that we remove the defective product from your pile of good parts. And the defects are 3D, so in the visualization you get is 3D. We can actually look at defects in 3 dimensions, and you can compare it to the tube and verify that it's real. For measurements, laser line triangulation just gives you accurate measurements regardless of shape and orientation, so it does not suffer from shape error like vision systems and laser micrometers do. And you can directly measure aspects like circularity, height, width, features on a non-round part as well. It's reliable, so it's significantly easier to set up than a vision system or micrometer, because again, you're looking at dimensional defects. So if you know your defects are X, Y, Z, height, width, length, you set that threshold and you're off running. It's objective. There's no opinions. If you cross the threshold, it's a defect. Faster startup, so we can detect things that happen immediately. You're not waiting for an inspector to check them. Detecting smaller defects. Again, there's no dead zones like a laser micrometer, so you're not missing tiny defects. You're not relying on visual changes in the surface due to lighting, like vision. It's looking at dimensional changes. So you're just able to detect smaller things than ever before with laser line triangulation. And all this data can go into a process visualization tool. So you can visualize the process similar to how a laser micrometer is often used to visualize the production process. You can monitor the measurements against specifications, calculate statistics, log data, and use all of this for closed loop control so you can control the process. And all of this information can be sent to other equipment as well via OPC. And finally, FlawSense can be installed in multiple ways. We have an all-in-one mobile system, so you can wheel FlawSense from line to line. It's good for medical R&D projects. You have a bunch of different lines. You don't want to buy 10 different devices. You wheel it from line to line. Microspec used an all-in-one mobile system for their production process. We also have a variety of electronics packages, basically for dirty environments or clean rooms. We can handle all of it. Currently, our product measurement range is from 40 thousandths of an inch, 1 millimeter, up to 2.5 inches or 64 millimeters. And then we have a modular station. This is for heavier duty applications, or if the FlowSense head is never going to change locations, you can bolt it into the line. And again, we have all the options available. Same with the mobile solution. We have an offline linear slide, so we can put FlowSense on a linear slide, and this is good for batches of parts. So we can put a part into the machine, hit a button, FlowSense runs over the part and gives you a go, no-go signal, telling you if there's defects, exactly where they were, and making sure that you're only giving out good product. So this is good for R&D projects. You can help figure out, really dial in those settings basically with an offline system. And that's all I have. So if you have any questions, please visit us at laserlinc.com/defect detection. We will be at MD&M West 2026. So see us there to see this live. And yeah, now we will do question and answer.
Thank you so much, Chad. Before we get to our Q&A, I'd like to ask you all to direct your attention to our webinar survey, which is available next to the presentation window. If you close the survey, you can reopen the widget by clicking on the icon along the bottom of your screen. And again, thanks in advance for filling out the feedback form. Your participation helps us make these events better for you. And now on to the Q&A portion of our event. As a reminder, to participate in the Q&A, just type your question into the text box located next to the presentation window, or click the Q&A icon at the bottom of your screen. And if we don't have time for all the questions today, we will certainly share them with Chad, who can get back to you offline. So let's get right to it. I'm going to start out with a question from Vin, who asks, is the threshold defined based on an acceptable diameter, or can it be identified as a deviation from the continuous surface?
Yeah, it's a great question. The answer is both. And typical, like in a laser micrometer, you would be looking at a change in the diameter. We can do that with FlowSense laser line triangulation, but the real benefit of 3D analysis is that you can look at rapid surface changes. Mm-hmm. So the defect you're seeing here, this might not cause a diameter change, but it's still detectable because it's a rapid surface change.
Okay, keep the questions coming. Tim wants to know, what was the diameter of the tubing you measured for microspec, and what is the size range for your system?
Yeah, so the microspec product was around 0.1 inches in diameter, and our range, it depends on the model you get, but we have a 29 millimeter system, which can measure 1 millimeter diameter up to 29 millimeters, and a 69 millimeter system that can measure, I believe it's 5 millimeters up to around 69 millimeters. So those are the two options.
Terrific. I hope that answers your question. Keep them coming. This one from Paulo, who says, can you clarify your point about measurement values versus rotation angle? Are you physically rotating the part, or is that all done in software?
Yeah, so these were simulations. So it was done in software to simulate a real rotating part. And so you can expect the deviation to actually be worse than what was simulated, because again, we're not including any of the other inaccuracies of a laser micrometer, like the angle it's presented or calibration error is not included in those numbers.
Okay, thank you. This question from Nicholas, who says, this system is only for external dimension defects and measurements, correct? No penetration into layers of the material or the interior.
Yeah, that's correct. It is surface dimension defect detection, measurement, correct. It can be coupled with other equipment, like ultrasonics that can measure the wall thickness. You can couple FlawSense with an ultrasonic system and measure inner diameter by taking diameter minus the wall thickness in a similar way that's done with a laser micrometer.
Which leads us to this question from Stefan, as he wants to know, is it possible to measure the wall thickness as well as the outer diameter?
Yes, with other equipment like ultrasonics, it is possible. And LaserLinc does have a ID/OD wall system, so we actually can take a diameter device and ultrasonic device, couple them together to give you ID/OD and wall measurements.
Mm-hmm. Okay, keep the questions coming. We have time for a few more. This one from Rory, who asks, how much operator training is required to run FlawSense effectively?
Yep, so for every installation we do, we have 2 days of on-site support. And the first half day is setting up the system. The second half day is training operators. Day 2 is entirely running. So it's effectively a half day of training, and we're good to go.
Terrific. We have time for a few more. This one from Tom, who wants to know, can it find pinholes?
Yes, it depends on the achievable frame rate, the line speed, and the size of the pinhole, but yes, it can. That would be something we'd need to talk to you more about and really dive into the details about how small and how fast you're producing.
Let's wrap up with a question from Lorenzo, who asks, what does the setup process look like when running a new product?
Yep, so there's a few different ways to do it. First, if you know the approximate size of the defects you want to detect, you can set those manually. You can just set height threshold of X, Y, and Z. Or you could we have an automated setup as well. So you could put the product in, run over a section of good product, known good product, and our defect detection parameters will adjust themselves to not detect that product, but any further deviation would be detected. So it's an automatic setup method. But whenever you do find appropriate defects, if you're running a new product that's similar, you could just use those same defect settings or do the manual setup or the automated setup.
Terrific. And we got a follow-up question from Vin, who wants to know, have you previously used this system to assess surface roughness or analyze texture patterns? And if not, do you believe it could be suitable for such applications?
Yes, it can, and we have done that before. I remember actually measuring the surface roughness of a catheter and comparing it to a competitor. And what we did was we put the competitor part in, and we had auto setup determine the surface variation. So it set up the defect detection settings automatically. Then we ran the new part, and we saw everything that deviated further than the competitor part. So it was a really good way to see how many points actually were beyond the threshold, and all those points were rougher than the other part that we calibrated the system with. So yes, we've done it, and it really depends on the level of surface roughness you're looking at, but it is possible.
Very cool application. And with that, that's all the time we have for questions today. I want to thank you. We appreciate your time and expertise on today's topic, Chad. Thanks also to our sponsor, LaserLinc, as well as to all of you in the audience. Thanks for your attention and participation in both the polling questions and in our Q&A. And within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to share it with your colleagues and peers who might not have been able to join us live today. On behalf of our guest, Chad Walker, I'm Michael Krieger. Thanks for your time. Have a great day.
Thank you.